right? And let's go in one deeper level. So does everybody know what this does and why it's useful? It computes eigenvalue of the matrix. Here, the eigenvalues of the matrix is 7.8 minus 1, 1, and 0.12. What does that tell us? Yes, it's the 7.8 that makes it blow up. And actually, if I take this eigenvalue, take it to 1/28th power, it actually gives the magnitude of this matrix. Why is that? In a very practical level, the biggest eigenvalue with the largest absolute value is basically the speaker for the matrix. I mean, it represents how the matrix is going to scale when you take it to the highest power. All the other eigenvalues doesn't even matter. Why? That's because when you take a matrix, you can do this so-called Jordan canonical form of the matrix, or basically eigenvalue decomposition of the matrix. You can write it as some matrix, square matrix, times lambda times U inverse. Okay, so don't care about the U's for now. It contains the eigenvectors of the matrix, which we will care about later. But this lambda, okay, this lambda here is actually a diagonal matrix containing these entries. It's like 7.8, 1, minus 1, and 0.2, while all the other entries are 0. So if you multiply two of these matrices together, what do you get? A times A is equal to U times lambda times U inverse, okay, times another U times lambda times U inverse. You know, in matrix algebra, you cannot switch two matrices in multiplication, but you have no problem actually putting the parentheses at a different place. So the good way to put parentheses is over here, right? What is U inverse times U? It's guaranteed to make identity. That's what inverse is defined, right? Okay, so that means whenever like U and U inverse is like a particle with this antiparticle, it's like whenever they meet, they vanish into nothing. So you get U times the square of this gamma, which because gamma is diagonal, you just have gamma square is just equal to square of this, right? And that's why you see when you multiply enough of this together, every time you multiply one, the U and U inverse cancel, and you basically get one more gamma lambda in the middle, right? So A cube would be equal to U times lambda to the cube times U inverse, and basically all these eigenvalues keep getting more and more power. At the end, which one wins? The biggest one, right? The one with the biggest the one with the biggest magnitude is going to dominate everything else. Like the ones and minus ones will be negligible as the 7.8 get a power of 128, right? So this, the top eigenvalue becomes about 10 to the 114, and the others is going to stay order 1, right? Or even smaller. So whenever you look at the eigenvalue of this stability matrix, what do you want to see? What would you want to see if you want a stable scheme?
See all of them were magnitude less than 1.
Yeah, you want to see all of them. So first of all, it's very clear you don't want to see things like that, right? You don't want to see any big numbers. How about if I get a minus 7.8? Would it be fine?
No.
No, right? Because minus 7.8 to the high power is the same, give me huge numbers, right? And what so what are the numbers? What are the type of numbers you don't want to see as eigenvalues of the matrix? Can you just give me one sentence that encapsulates what you don't want to see?
Any number larger than absolute value 1.
Any number whose absolute value is bigger than 1. That's something you don't want to see, right? Okay, another thing is when I take the eigenvalue of a matrix, am I guaranteed to get real numbers? No, right? That's basic linear algebra. So in general, I get actually complex numbers. So here is actually some special case. I get all real numbers. I'm surprised. Okay, if you get complex numbers, what can you tell me what you don't want to see? The modulus, right? You don't want to be larger than 1. In complex numbers, a general rule is lambda to the nth power. If you take the modulus of that, is actually equal to the modulus of lambda to the nth power. The modulus commutes with power. So if the modulus of an eigenvalue is greater than 1, then after you take the eigenvalue itself to the nth power, you get huge numbers. So in general, let's draw this. If you have real of lambda, imaginary of lambda, I can plot the eigenvalues of a matrix in this complex plane. And in general, I have more than 1 eigenvalues, right? In my previous case, I get a 1, a -1, something large, and something here, right? I mean, in general, I may get complex numbers like here and here. Where would you want all your eigenvalues to be?
In a circle.
In a unit circle, yes. So this is stable. If you see any number, not just the, if you see any number in the unstable region, you get an unstable scheme. All right. So that's why somebody last lecture asked me, okay, what if I try to derive a 6th order scheme, 8th order scheme? Would I be the same thing as a 4th order scheme I get unstable? My answer is very likely yes. Because the higher order you go, the bigger the matrix is, right? And the bigger the matrix is, the more eigenvalues you get. And it's quite likely you get some eigenvalue outside this unit circle.